Thank you, everyone, and good afternoon. Generally speaking, spaceborne data isn't something that's widely discussed when it comes to the mining industry, but hopefully we're here to change that today, and there's some pretty awesome innovation that we're bringing to the fore. So let's talk a little bit about Pixxel. The company was established in 2019, and the engineering philosophy and the thesis at that point was that open source data from space isn't providing us the level and the richness and the depth and the rigor of information that's actually needed. When we looked at what was available out there, we noticed that there were three major gaps. One was the spatial resolutions were really coarse. In other words, open source data was giving us information at 10 to 30 meters, which is not granular enough to be able to resolve certain properties. The second big gap was the spectral resolution. We noticed that most of the satellites could give us information in RGB, in other words, what your naked eye can see, right? So you can see shape and color and object, but you can't really see spectrally things like chemical changes or biophysical changes. You can't even look at a lot of infrared signals that might, for example, give you indicators of air quality or water quality. And breaking the light up into hundreds of different wavelengths, especially on the invisible side of it, was something that was missing. So that was the second big gap. And then the third big gap was the temporal resolution. Most satellites were imaging every 15 to 30 days, and that was only if you were lucky, if there were no clouds. So those were the three big gaps, and that's why we realized that we wanted to build the world's first and highest resolution hyperspectral constellation that would be a true health monitor for the planet. In other words, being able to track all the important vital indicators that were necessary for us to make informed decisions and actually learn about the environment and the situations around us. We realized that in order to make this a viable business, there were four things that we really needed to get right. The first one was we truly needed global coverage, so anybody should be able to task our satellites and be able to access even the harder to image areas. The second one was that we needed the right spatial and spectral resolution combination. So our satellites are designed to collect data at a 5-meter resolution and 250 bands. So we would cover the visible near infrared as well as the shortwave infrared ranges, and we'll take a look at how that translates into mining applications next. The third aspect was to have daily global access, which means have a 24-hour revisit, which means that when there are time-sensitive changes that occur, for example, in the case of tailings ponds and mining, where you need very, very rigorous daily monitoring, it's really important to have a frequent enough revisit so that you can have change detection that actually matters and it's delivered at the right time. Else, if that insight is delivered at the wrong time, it loses all of its value. And finally, we needed to have a compact form factor because we needed to make the cost of this not prohibitive for the big industry players to actually buy this level of data at this scale. So this is a visual example of the power of hyperspectral. That's an image of Lake Geneva that has been taken using conventional satellites. So you can see, for example, the basic features, right? You can see the land around it, you can see the blueness in the water, etc. When the same area is now imaged using a hyperspectral sensor, you're able to start taking a look at the chemical properties, which is stuff that you can't see with your naked eye. So you can see here if there are any kinds of algal blooms, you can see contamination levels, you can see the chlorophyll content, you can see the chemical oxygen demand. All of this stuff becomes visible with hyperspectral because the technology splits up light, visible as well as invisible, and collects 250 different channels of information, right? So that's really the power. And you can get this using a drone with a hyperspectral mounted sensor, but it's not scalable, it's super expensive, and we need something that's truly repeatable and affordable and works at scale. So bringing this level of spectral richness from space is really what hyperspectral can do. As you can see, that's the visible light spectrum, and this is the Sentinel-2A band response. So you can see, for example, that there's a very limited number of responses, right? And the distance between the bands is very wide, which means there's so much information in the middle that's actually getting missed out. Whereas with Pixxel's 5-meter hyperspectral band response, this is the information richness, right? So you can see the density of information, you can see minor changes, you can compute narrowband indices to be able to look at what materials are present spectrally, what chemicals are present spectrally as well. And then imagine coming having that on a 24-hour revisit with global coverage. So that's the power of the Pixxel constellation. This is finally what sets us apart. It's 50 times more information than most satellites out there, and it's 10x lower costs because we've been able to compact this in a form factor that looks like a mini fridge. So it's a 50 kilo satellite with this level of computation and imaging power. We image in the 470 to 2500 nanometer wavelengths, and we'll take a look at what that actually means. But when it comes to detecting iron oxides, rare earth elements, ore bodies, coming up with a spectral library of most of the minerals that are out there, looking at water quality indicators, vegetation changes, and air quality indicators. All of these buckets are covered in the 470 to 2500 nanometer range, and it's all happening at a 5 meter resolution. What makes it even more unique is that it's a 40-kilometer swath, which is the width at which we image, so you can cover very large areas with the whole constellation and deliver this level of richness. We've proved out the technology because we've been operational since 2021. Actually, we've flown 3 hyperspectral proof of concept cameras, and we flew them at a 30 meter, 20 meter, and 10 meter resolution. They were all collecting over 150 bands. And these satellites have now reached their end of life, and we've generated a pretty big archive, so we'll show you what the applications in mining are as well. And some of the areas that we've imaged might be quite familiar to everyone here in this room. We're launching our flagship constellation of 6 satellites in January this year, which is why it's timely to meet all of you. So it's going up in less than 3 months now with SpaceX Transporter 12 from Vandenberg. We're also launching our first shortwave infrared tech demo, and finally we'll have an 18 satellite constellation that is completing in 2027. By the way, with the 6 satellites that launch in January, we'd already have global coverage and 72-hour revisit. This is the advantage of hyperspectral data in mining. You're able to start looking at mineral composition, so do true mineralogy. You can start discovering new materials. You're able to manage tailing ponds, which means that we can actually start looking at hazardous leaks in terms of the changes that they show up in the vegetation, the way the soil chemistry changes, the water quality in and around it. We're able to do site assessment and feasibility. We're able to do geotechnical stability as well as land rehabilitation. Which basically means from the time you actually start exploring all the way to closing out the mine site and handing it over for the next sort of 10 to 15 years, where it has to be monitored for its environmental impact and it has to be monitored for due diligence, etc. We have the entire value chain covered. So a picture space says 1,000 words. So these are some images from our own Pathfinder satellites. So these are from the Pixxel satellites that we've operated over the last 3 years that we've imaged certain locations. The first question really for us was, could we get a response with hyperspectral? So could we get a response in space from a lot of the minerals that were present? Because the atmosphere actually muffles things up a lot. So with good atmospheric correction, we were able to get a positive response for hematite. So we ran this with the spectral libraries that were available within NV5 and a lot of the well-established spectral libraries to correlate our wavelength and to be able to check for accuracy. And we were able to verify a hematite signature or hematite signal, right? So we could really spot it. And this is in the Brockman 4 mine in Hammersley. The next one was the stability assessment in Namibia. So we were looking at a particular site to be able to assess the soil conditions, just the environment situation, so the kind of vegetation around it and any kind of geological features that might be interesting, to be able to look at the land and the stability characteristics for site planning and better construction. So again, these are, they are incredibly pretty pictures, but there's a lot of science within them as well. So towards the left is the hyperspectral stamp, and towards the right is a basic RGB stamp. So you can see how much more richness there is. For every color that you're able to see here, it's actually a pretty dense spectral cube. So that's a 3D cube of tons of spectral responses. So you're able to see that level of information here, and each and every color is a false color composite that indicates a different pattern or a different material that is present. We're also able to look at water quality monitoring. So, and we have a ton of early adopters behind this because we're able to scan the surface again for chemical properties. So we're able to look at any kinds of events that might be interesting. So pollution levels, turbidity, algal blooms, chemical oxygen demand, any kind of contamination from a quality standpoint. And this becomes really important as well because when we're looking at situational awareness and getting smarter from space, imagine being able to get a sense of this every day, so you can take a look at what the runoff is in the water, which means that if there is runoff that you're able to spot in a water body that might be located close to a particular tailings dam, then you're able to create a certain level of attribution about whether something's leaking or not. Right, so there's all these different proxies that we can start spotting from space that might indicate whether a particular site needs special attention or whether you need any kind of operational intervention. Usually, this costs hundreds of thousands of dollars per pass. It's done with a handheld drone or it's done with an airborne camera. So hyperspectral technology isn't new. It's existed in the field of medicine before. It has existed in laboratories as well. But it's just super expensive to administer every day, and as a result, it's operationally very inefficient. So our big innovation is bringing that same power and resolution from space. So you can actually do it at scale, and it can be completely repeatable. On the right here, you're able to see different anomalies, right? So you can see the scale of this going from 0 to negative 4.5, from yellow all the way to the dark blue. And you can take a look at particular characteristics along the spectrum as well. So the anomaly detection in the case of pollutants and quality indicators is the highest in the darkest areas of the blue, which is where you can see, and this is Utah Lake in the US that we looked at. This is a mine in Chile where we were looking at lithium ponds detection. So it's an example of material identification. If there were tailing sites nearby, then it can tell you things as well. The use case behind this actually was for operational intelligence, for better sort of material readiness and dispatch and shipping. So we could see the volume and the geographic extent of the brine pools. We could see the concentrations within them. We could look at impact to the surrounding area to make sure we minimize any kind of environmental externality. And that's really the purpose for which we were monitoring this area. And finally, this is tailings and waste management. So when combined with synthetic aperture radar, you're also able to get moisture indicators. So hyperspectral is not necessarily the silver bullet. It is probably one of the most diverse data sets that we're bringing from space, but we can fuse it with other data sets as well to be able to deliver that absolute nugget of intelligence. So it works really well with synthetic aperture radar that is able to see through canopies or that's able to see through surfaces. And then with our spectral fidelity, when we're able to detect hazardous materials and chemicals that actually end up leaking out, it becomes a pretty powerful value proposition. And then we were finally able to do some land surface classification. So we looked at a maximum likelihood classification that was done over this scene. I was using the geological maps of Nevada. And we were able to separate basalt flow and sedimentary flow as well. So we were able to look at marshy areas and also areas that had high levels of sedimentation. And while there's some minor confusion between alluvial deposits and sedimentary stuff, we're able to separate it using hyperspectral. That confusion is otherwise not resolved in multispectral data sets, where the bands are just too far apart and there's not enough information or context in the middle. So this way we can directly attribute cause and analysis and provide very clean images where you have a 1:1 correlation between a cause and an effect and a certain variable and its signature. So yeah, that's just what we wanted to share today, and we're around for the next couple of days. My name is Aakash, and very nice to meet all of you. Thank you.